Good morning. I'm going to go ahead and start. Okay, so we're going to continue the review of aldehydes and ketones today. Last time I went over nomenclature and so today we're going to look at some of the reactions of aldehydes and ketones. Okay, first of all, we'll look at the Grignard reaction. Okay, let me adjust the camera here. There we go. The Grignard reaction. All right, so take out a sheet of paper and something to write with. Okay, so show me the mechanism for this Grignard reaction. Okay, so we have benzaldehyde, and we're going to react it with phenyl magnesium bromide, followed by hydrolysis. And I'll give you just a minute to work that out. Okay, so the carbonyl is polarized, the carbon end is plus, nucleophile. Okay, this carbon is now negative. We'll attack the carbon nucleus. Okay, so the arrows show movement of electrons, not atoms. And we form a bond from C to shining C. That's a new carbon-carbon bond. Right, and the electrons move toward the oxygen, so it's now negative. All right, so when this reaction is complete, then we add dilute acid. Okay, so this will go in and pick up a proton. Okay, this is our product. It's diphenylmethanol. Excuse me. Okay, so in that reaction, our starting material was an aldehyde, which would give us a secondary alcohol. Formaldehyde would give us a primary alcohol, and any ketone would give us a tertiary alcohol. Right, this question is just a reverse of what I just showed you. Okay, so here's the product, and I'm asking you, what starting materials would you use to make this using a Grignard synthesis? Okay, so this is working backwards from mechanisms such as the one we just saw. Okay, so working backwards, we locate the CO bond, and this is symmetric, so there's really only one way to make this using a Grignard. Okay, so we locate the CO bond, and then we break the next carbon-carbon bond. Okay, so in forming the alcohol, we form a new carbon-carbon bond. So we're going to break this bond. And the part without the oxygen would be our Grignard. So this would be ethyl magnesium bromide or chloride. Right, then the part with the oxygen. Okay, we would keep this H, take away this H and make it a double bond. Okay, so it would be ethyl magnesium bromide and propanal. Okay, so here's one pentanol. Same question. How would you make this using a Grignard synthesis? Okay, working backwards, this is a primary alcohol. Okay, we locate our CO bond, and we break the next carbon-carbon bond. And so the part without the oxygen has 1, 2, 3, 4 carbons. Okay, so that would be butyl, magnesium bromide or chloride, and then this part would be formaldehyde. At the end of the last video, I briefly reviewed what a hemiacetal was. A hemiacetal is a compound that has an alcohol and an ether on the same carbon. Most hemiacetals are not stable. If they're formed in a reaction, they immediately lose the alcohol group and go back to the original aldehyde or ketone. An exception, though, is if we have a 5 or 6 membered ring. Okay, such as this. Okay, in this case, the cyclic hemiacetal is actually the favored favored form. Okay, so this is in equilibrium with, and this would be the alcohol part, or the ether part, the alcohol part, and then we would have an aldehyde since there's an H here. Okay, so the mechanism of formation, this requires either an acid or base catalyst. Okay, so I'll go through the mechanism. If we have an acid catalyst, right, the first thing that happens is that carbonyl oxygen picks up a proton. Right, and then the alcohol uses its lone pair to attack. Right, the electron's moved away from this oxygen. It has 3 bonds now, so it is positively charged. Okay, this oxygen was positive. The electrons moved toward it. Now it's neutral. And then in the last step, water takes this hydrogen. Okay, so we've got our hemiacetal, and water gains a proton, so it becomes H3O plus. Okay, so by definition, a catalyst emerges unchanged. Okay, so that's formation of a hemiacetal, and again, this is an equilibrium reaction, so the ring does open and close, but the favored form is actually the cyclic form. Larger or smaller rings than 5 or 6 membered are not favored. Right, an acetal is defined as a compound that has 2 ethers on the same carbon. Acetals are generally stable. If you form a cyclic acetal, it doesn't equilibrate with the open chain form like the hemiacetal does. Acetals can be removed by dilute acid. Okay, so this will go through a hemiacetal. Let's take acetone, and I could use 2 alcohols, or I could use a diol. Okay, first of all, I'm going to show you a shortcut. Okay, say we had methanol here. Okay, I'll show you the shortcut and the mechanism. Okay, the shortcut is that we lose water. Okay, so if you line up your alcohols like this and split out water, Okay, we get this acetal, which is, this would be 2,2-dimethoxypropane. Right, next I'm going to show you mechanism for acetal formation. Okay, I said H plus instead of H3O. You don't want a high concentration of water. Typically, you use an organic acid in a non-aqueous solvent. Protonate this oxygen. And I'm going to use ethylene glycol, or 1,2-ethane diol. And so one of the alcohol groups here will attack. Okay, and then you have a transfer of protons. In reality, probably the solvent is going to take this, and then this will take it from the solvent. I'll show a shortcut here. Okay, this probably doesn't happen intramolecularly. Right, and then water leaves. Write this up here. And then this OH will attack, we'll remove a proton, and then our final product will be this cyclic acetal. Okay, acetals are very useful as protecting groups. Okay, we can form an acetal to block or mask a aldehyde or ketone that would otherwise react, and we could carry out our reaction and then remove the acetal when the reaction is finished. Okay. This is a problem where we work backwards. Okay, so here is the acetal. And what is the aldehyde or ketone? And the in this case, it would be a diol since it's cyclic. Okay, so what are the starting materials for forming this acetal? Okay, so we locate the carbon that is connected to two oxygens, and I'll give you a minute to see if you can work this one out. Okay, there's an H here that's implied. Okay, so what is the diol and what's the aldehyde or ketone that we start with to make this? Okay, you may remember in the shortcut, we took out water. So in this case, working backwards, we're going to put water back in. So we'll break this bond, we'll break this bond, and we have, okay, so this would be 1,3-propane diol. Okay, so that would be our diol. And ethanol. Okay, so we put back H2O. Working this way, okay, we would split out water. Okay, same question here. What starting materials would you use to make this acetal? Okay, so we could disconnect both of these CO bonds. Okay, so that would be 2 ethanols. And our other starting material would be cyclopentyl methyl ketone. Okay, next we're going to move on to nitrogen nucleophiles, ammonia and amines. Okay, in this case, I'm not going to ask for the mechanism, but just the product. Okay, so suppose we have cyclohexanone, and we react it with cyclohexylamine. Okay, and this requires just a trace of acid catalyst. Okay, you don't want to get it too acidic because remember amines are basic, and that would simply convert the amine into its conjugate acid. Okay, just a little bit of acid to catalyze this. Okay, so what's the organic product? Okay, I'll I'll give you a hint. Byproduct would be water. Right, there's a shortcut for this, just like we had for the acetal. Okay, we're going to split out water. And we'll replace the CO double bond with a CN double bond. All right, this functional group is called an imine. And imines can be reduced to amines using, for example, hydrogenation. Right, this would add a hydrogen to each side. Okay, and there's various amines that we could use. If we used we could use ammonia. That would produce a primary amine. Okay, we're starting here with a primary amine, so we get a secondary amine. Okay, this reaction can be reversed. This reaction right here, the imine. Okay, here we have a trace of acid. If we use H3O plus, okay, we can reverse it. We can take it back to the ketone. Okay, the mechanism involves several steps. Okay, the carbonyl amine, okay, where we have an OH and an amine on the same carbon. Right, this is an intermediate, but it is unstable. Okay, instead of losing water, I'm sorry, instead of, well, it does lose water, but instead of going back to the original aldehyde or ketone, what happens is it does lose water, but it goes on to the imine. Okay, next I want to look at oxidation of aldehydes and ketones. Okay, ketones are not easily oxidized, but aldehydes are very easily oxidized. Okay, so here we have benzaldehyde, and if we oxidize benzaldehyde, what is the product? Okay, and this can even be done with oxygen in the air. Show me draw the product. Okay. Cool. I'm so used to the interactive activities where I can see what your answer is. Okay, what would the product be? Okay, the oxidation product of an aldehyde is a carboxylic acid. Okay, we can also use other oxidizers. We could use chromic acid, okay, which is a strong oxidizer. We could use potassium permanganate. These are both strong oxidizers, but even mild oxidizers like you could use silver ion, Ag+. Okay, what happens here is that the aldehyde gets oxidized, silver gets reduced to silver metal, and so you end up plating a layer of silver on the test tube or flask. Okay, this is also a good simple chemical test for an aldehyde. Okay, ketone won't react. Ketones are quite a bit more difficult to oxidize than aldehydes are. Okay, next we'll look at reduction. So here we have an aldehyde, butanal. Okay, and there's a couple of different ways that we can reduce this. Okay, I was just talking about oxidation. If we oxidize an aldehyde, we get a carboxylic acid. If we reduce an aldehyde, that will take it to a primary alcohol. So a couple of different ways we can do this. We can use catalytic hydrogenation, okay, hydrogen in the catalyst. That will add an H each side of the double bond. So butanal would become 1-butanol. We could also use sodium borohydride, NaBH4. The mechanism for sodium borohydride reduction, go ahead and erase this, is actually very similar to that of a Grignard. Okay, so the carbonyl is polarized, the carbon end is plus. And unlike something like HCl, where hydrogen is partially positive, in this case, hydrogen is partially negative. And so hydride acts as a nucleophile. It attacks the carbonyl just like a Grignard does. So we add a hydrogen, and then the H for the alcohol usually comes from the solvent. This is done in either water or methanol or ethanol. Okay, so let's say we're doing this in methanol. We'll pick up an H from the solvent. And our product now is 1-butanol. Okay, while an aldehyde gives a primary alcohol, a ketone will give a secondary alcohol. So we have cyclohexanone, which is a ketone. Okay, if we use hydrogenation or sodium borohydride in, say, methanol, Okay, we'll convert cyclohexanone to cyclohexanol. Okay, what if we also have an alkene present? Okay, so this would be X3-ene 1-one. Okay, hydrogen and a catalyst would reduce both the alkene and the carbonyl. Sodium borohydride just reduce the ketone. Okay, and then the last thing from this chapter, and that is I'm going to review tautomerism. And specifically the tautomerism between ketone or aldehyde and an enol. All right, so that's a ketone, and this is an enol. Okay, and notice which way the equilibrium is shifted. It's toward the ketone. Okay, an enol is a compound where you have an alcohol directly on an alkene group. Okay, most enols are not stable. There are a few rare exceptions. Okay. All right, let's move on to the next chapter. A few minutes remaining. Okay, enols are important intermediates if you want to do an alpha halogenation of an aldehyde or ketone. All right, moving on to the next chapter, which is carboxylic acids. All right, let's start out with naming. All right, name this carboxylic acid. Okay, so 6 carbons. So that's hexane. We drop the E, this becomes hexanoic acid. And it would be 4-ethyl. 4-ethyl hexanoic acid. So draw 4-oxocyclohexane carboxylic acid. Right, so cyclohexane. And carboxylic acid can't be part of the ring, which is why we don't say cyclohexanoic acid. So this accounts for the extra carbon. Okay, unlike the open chain carboxylic acid, instead of this being carbon number 1, this is carbon number 1. So 1, 2, 3, 4. Oxo is a ketone as a substituent. That's 4-oxocyclohexane carboxylic acid. Okay. So draw benzene 1,2-dicarboxylic acid. Okay, and it would not be correct to call this dibenzoic acid. Okay, this is commonly called phthalic acid, which is PH, TH, ALIC acid. It's an important industrial starting material for making polymers. Okay, the next one is 2-pentenoic acid. Okay, pentenoic acid. And let's make this trans. Okay. Pentane is 5. so we would have an alkene between 2 and 3. This would be the trans. Carboxylic acid has the highest priority of any functional group as far as naming. Okay, what's the name of this? Four carbons. So that's butane. We drop the E. This becomes butanoic acid. And it would be 4-hydroxy. Okay, it would not be correct to call it 4-all butanoic acid. You would only use all if the alcohol was the dominant functional group. Okay, be familiar with groups and properties that will affect acidity of carboxylic acids. One of the most notable properties of carboxylic acids, of course, is they are more acidic than most other functional groups. Right, if there are nearby groups that would withdraw electrons, such as halogens or nitro groups, okay, those tend to make carboxylic acids more acidic. Right, we can form the conjugate base of a carboxylic acid with hydroxide. You can also use a weaker base like sodium bicarbonate. Byproducts would be water and CO2. Okay, carboxylic acids are typically 100,000 times more acidic than phenols. And while hydroxide could deprotonate a phenol, phenol won't react with sodium bicarbonate. Okay, so you can selectively separate a carboxylic acid from a phenol using sodium bicarbonate. Okay, so that's all of our time for today. So next time, we'll look at functional derivatives of carboxylic acids.